the first question is about uniform circular motion. Uniform circular motion is a kind of motion in which when an object moves in a circle, its speed does not change with time, so it's constant speed. But since it's a circular motion, so direction of velocity can change, and that's why it's called uniform circular motion. So our first question, so this is the first one, and we have a semi-circle here, something like this, and then we have a car, and we have three different locations of the car, and we have been asked what will be the direction of velocity vectors for these 3 points. These 3 points represent the car's motion at 3 different times, and since the car moves with uniform speed, and I have just said that it's a uniform circular motion, which means that the speed doesn't change, but the direction of velocity can change, and that's what you are asked to figure out. Some of you might wanna, relocate yourself so that you could face me instead of turning your necks 180 degrees. That will be painful in long run. So what do you think? What will be the direction of velocity vectors in at these 3 points? I guess I had briefly talked about this thing in our last class too. That how the direction changes in circular motion. What do you think? Where should be the direction for this point? It should be tangential to this point, and a tangent point is a point which touch a line or a curve at only one point. Okay, so if you have to draw a straight line which touch this curve, this circular path at only this point, then it will be a tangent line, and the line will point in this direction. Okay, so let's use blue. So this will be the tangent line, and this will be the direction of velocity vector. So let's call it V1, corresponds to first time. And then for this one, again, it will be tangent, and the tangent direction will be this one. So let's call this V2. And at this point, it will be in this direction because this is the tangent direction, and let's call this V3. And since it's a uniform circular motion, so it's V1 equals V2 equals V3. That means the magnitude or speed of the car does not change around this loop, but its direction can change. And the acceleration, its definition is change in velocity divided by the time in which this change in velocity occurs. And if we call delta V as the velocity at 2 different points, V2 minus V1 divided by delta t, the time in which the object speed goes from V1 to V2, then this is the definition of acceleration. And if we want to look at the direction of acceleration, by definition, you can see that the acceleration, it depends on, since time is always positive, it basically depends on velocity vector. And velocity vector, since it's a vector quantity, it can change in 2 different ways. The first way is that its magnitude can change, direction doesn't change. The second way is its direction changes, magnitude doesn't change. And the third possible way is that both direction and magnitude changes. In this scenario, we see that as the object, the car goes from this point to this point, the velocity stays same. At 3 different points, the speed is same. But the direction changes. It means that the acceleration, its direction, and its complete value, like the magnitude and direction, it should come from that change in direction of velocity. And that's your second part. Like what will be the direction of acceleration at the top of this circular path? So this is the top. So what you do to calculate the direction, so you take this velocity vector and translate it like this to this point. So now this is V1 and blue one is V2. And you can see that the difference as the object goes from V1 to V2, this is the change in direction, this green one, okay? So this green one is delta V, and this direction is perpendicularly downward. So this is the scenario at the top. It means that the direction of acceleration is downward. So this is the direction of acceleration. Okay, that's how you calculate acceleration in a uniform circular motion. And this is the general case, like you pick any point and the direction will always be pointing towards the center of this circle. Like if you were to complete this circular path into, let's say, some sort of circle, okay, because this is part of some circle. And if you were to complete it, and then if you were to check the direction of acceleration at this point, when the car is at this point, you would find that the direction of acceleration turns out to be this one, exactly by adding two different velocity vectors. And if you were to calculate at this point, you would find that the direction of acceleration is towards this point. Meaning that all these arrows which represent the direction of acceleration at different points on this circle, they will all point towards the center. And that's the basic definition of circular motion. Okay? Circular motion is the motion in which acceleration is always directed towards the center. Specifically uniform circular motion, in which the velocity of the object does not change with time, but its direction can change. And that change in direction gives us the acceleration, which we can see from this diagram, always points towards the center of the circle. Okay, so this is a very important line, that the direction of acceleration, it always points towards the center of the circle, which means you pick any random point on this circle, the acceleration will be towards the center of the circle. Okay, this is very important. It seems like at this point it's going somewhat in the upward direction. At the top it's coming perpendicularly in the downward direction. The only thing these arrows are doing, they are pointing towards the center of the circle at all times. That's what is important about this kind of motion. The next part is to the right. Draw a free body diagram of the car at the top of the hill next to the free body diagram. Indicate the direction of net force on the car, or if appropriate, write F net equals 0. Okay, so here's the scenario. We are supposed to draw a free body diagram of this point, which is pretty easy by this time. You know that I have already represented car by a point, so it already is kind of a free body diagram. And we know that the weight of the car, it will always be downward for obvious reason, because this is because of the force which Earth exerts on the car. And then since it is on this curved path, some kind of road, the road will exert a force on this car, which will be normal to the point, this point, at the instant at which the car is at that point. And then the sum of these two forces, normal force and the weight of the object, it should give us the net force which an object feels when it moves in a circular path. And that net force is mv squared by r. That's what you study. Like when an object moves in a circle, the kind of equation that it follows is like sum of all the forces that act on the object, they should be equal to mv squared by r. Okay. Now you can see that the forces that the object feels, there are two forces. Normal force, which is if we choose this coordinate axis, positive y, positive x, then normal force is toward positive y axis. So I'm gonna take normal force positive, and then weight of the object negative, equals mv squared by r. Okay, but this is not what we have been asked in the question. The question asks what will be the direction of net force. Can you from this equation tell me the direction of net force? It's actually that first part that gives you a very big hint what should be the direction. Here we have just seen it pictorially. Here we are going to answer the same question mathematically. We have seen here in this observation that there is a non-zero acceleration, and the direction of this non-zero acceleration is towards the center of the circle. Now Newton's second law, F equals ma, it tells us this: if A is non-zero, then the force is gonna be non-zero. Okay, this F equals ma that you have studied very well by now. This tells us that if acceleration is non-zero, the force is gonna be non-zero. Okay. Additionally, whatever direction acceleration has, the force is going to have the same direction. Okay, which means that in this case, in this question which have been asked from us, force will be non-zero, and its direction shall be the direction of acceleration, which is downward. And here we have defined a coordinate system in which downward direction we have chosen to be negative, because positive y-axis is upward, so downward direction is negative. It means that we have an acceleration here, we have a non-zero force here, and the force is directed in the downward direction. Okay, let's write this equation in a different way. Let's write it W minus N equals minus mv squared by r. Now this gives us that since this was equal to force, so this negative right hand side tells us that this negative sign actually represents in the direction of the force, which is downward. Difference of these two forces can give us a negative answer only if weight is if normal force is greater than weight. So you also observe from this point that at the top normal force should be greater than the weight of the object. And this is very important because this is our next question. What happens if normal force starts decreasing, it goes to zero? What happens then to the car? Okay, so now we have some non-zero normal force and the car is always on the surface of this circular path. What happens in your experience, you might have seen in movies or may have experienced this yourself if some of you are adventurous. What happens if you go at very high speed on such kind of curvy roads? Have someone ever not slowed down at a speed breaker? You just felt like, I'm gonna go at 70. You would see that as you go over the speed breaker, your car jumps. It do not go peacefully on the other side. Okay, this is because in that case the normal force becomes zero and your car is no longer in touch with the ground. So this is our actually next part of the question. So if normal force becomes zero, it means that there is no connection. How do we get the normal force? Normal force is the force which two surfaces exert on each other when they are in touch with each other. Okay, I put my pointer here, so there is a normal force which is exerted by the table on the pointer. Okay, but what happens if I lift the pointer? They are not in touch, and so normal force has gone to zero. Same case is here. If there is no normal force here, which means that car is not in touch with the road. Okay, so in order for the car to stay on top of the road, normal force have to be non-zero. And as you increase your speed of the car, normal force starts decreasing, and there comes a point when normal force is zero. And when the normal force is zero, car is no longer in touch with the road. So there should be some limit on the speed, like the maximum speed which you can give to your car, such that the car is still in touch with the road. It doesn't go off the road. Because if you're gonna give it like a huge amount of speed, it's gonna go off the road and then the normal force goes to zero. That's exactly our next question. What is the maximum speed you can have on top of this road such that your car is still barely in touch with the road? Like you do not just fly off the road. Okay, so that situation you substitute normal force to be zero, and when you substitute normal force to the zero, you get the value of velocity to be v equals, it's a magnitude of velocity, r times g. This is very interesting result. Okay, so how did I get this? I substituted there normal force to be zero, weight is mass times small g, and so mass cancels, and then I solved for v. And I have written magnitude because there was a negative sign. Negative sign just tells you the direction of the force at the top. So we are talking about speed, that's a scalar quantity, and that's why I took the magnitude. Okay, this is the maximum speed that your car can have and still be on top of the road. It will not fly off the road. What if you drive a bicycle? That's something that you can infer from this mathematics. It's a very important point. That's actually how we do infer all the things about the objects that we see around us just from mathematical equations. This is the first hint. I want you to take a look at this equation and try to answer this question which I'm asking. What if you are not driving a car? What if you are driving a bicycle? Would it matter? Would the speed be different? Let's say your car goes off the road at a speed of 45 miles per hour. Now I change the question and ask you, what if you are driving a bicycle? Would it still go off the road at 50 miles per hour or at any different speed? What do you think? How do you get this information? How do you get to answer this question? You look at this equation. Okay, your speed, the maximum speed which you can acquire and still be on the road, on top of the road, like you do not fly off the road. This is the maximum speed. And then you look at the right hand side, this speed depends on two factors. One is acceleration due to gravity, value is 9.8, it's a constant on Earth, anywhere. Okay. And the second thing is R. This R is actually the radius of this circular path. If this is the center, then this is R. So given a road, a curve in the road, R is also fixed, which means your speed depends only on two constant factors, two pre-decided constant factors. G is constant, you cannot even change, and R is the radius of that curve, which you fix when you construct the road. Okay, once you choose the road, like I'm gonna drive on top of this curvy road, R is also fixed. It means that it doesn't matter what you drive, car, bus, bicycle, motorbike, whatever. If you go over, let's say 50 miles an hour, you're gonna fly off the road. It doesn't matter if it's a bicycle or if it's a car. And that's what mathematical equations tells you. If I had a factor of mass here, then what you drive would have mattered, because then the mass is the mass of the object that you are driving. So if you drive a car, that's a way more massive than a simple bicycle, and then so speed would be dependent on the mass of the object. But since we have seen here that speed is totally independent of the object which you are driving, it doesn't matter you drive a bicycle or you drive a car or you drive any other vehicle. The speed is fixed. Speed is fixed by the road. Once you choose the road, if you go over 50 miles an hour, your vehicle is gonna fly off the road. That's it. Okay, so that's the three parts. That was part C. And part D is there a maximum speed at which, actually I just answered this part D. I don't know what is part C. So does the net force of your free body diagram point? Okay, point C is just the confirmation. It just tells you that in this part, if you have found the direction of force different from this part, then you must have done something wrong. So go back and recheck it. And this is what I argued, since acceleration is directly proportional to force, and the direction of acceleration is actually the direction of force, and we have seen here that the direction of acceleration is downward, so the direction of force should be downward. So in this free body diagram, net force should be acting downward, and that's what I have argued for. And then part D asks for like the maximum speed that you can have and still not fly off the road, and that maximum speed is R times G. It's totally independent of what you are driving. Okay, questions related to this one? No? Okay, second question is force in circular motion, and this is exactly similar to this one, with the only difference that in this case we had a road. In second question, you are just you have attached an object, a mass, at the one corner of the string, and then you make the string go in a circular path. That is like you have some mass, and then you have attached it to some string, and then you let this go in a circular path. And the question asks you a couple of different questions. Let's make it a circular path. Okay, so this is circle in this case. So the only difference of this question from the previous one is that in that case we had normal force. In the case of string, the normal force is replaced by tension force. That's just the different forces which act between different objects. If you take a string, a wire, or anything, the force is going to be called tension force. And if the two surfaces are in contact with each other, the force is going to be normal force. Otherwise, the situation is totally same. So let's analyze the motion of the object at the top of the circle first. This is center of the circle. So tension force, it attracts the object, pulls the object in the downward direction. Weight of the object is also in the downward direction. And this equation tells us that the sum of these two forces should be equal to mv squared by r. Again, you need to choose your coordinate system. Let's choose positive y-axis upward. And so for this case, the equation summation f equals mv squared by r will become, now sum of both the forces is in the downward direction, so we will have w plus t equals mv squared by r. This is the scenario at the top. You just are supposed to write the equations. Okay, what will be the situation at the bottom if when this mass revolves, half circle comes here? It is string still attached to the string. So in this case, the situation will be like this. So this is the string, tension force pulls it in the upward direction now. Weight will be in the downward direction, and the force, this force mv squared by r, this will be in the mv direction. So in this case, summation f equals mv squared by r will become, now you see T is in the positive y direction, so tension will be positive in this case, so this will be T, but the weight is in the downward direction, so this will be T minus W equals mv squared by r. So that's the difference between these two equations, and that has some effects on the speeds of the object, like with which maximum or minimum speed they will cross the top of the circle and with what speed they will cross the bottom of the circle. You have questions related to this one? You just define your coordinate system and then you draw the direction of forces, which you already know. Tension at this point, it's in the downward direction, because if you are revolving this, setting this object into circle by applying a force from your hand, then this tension force is the force that you are giving it to with your hands, with your arms, okay? And since it's towards the center, so it's downward. But at this point, the center lies in the upward direction. That's why the direction of tension force has changed. But weight, since it's always in the downward direction, so it's downward direction here, it's downward direction here. And that downward direction changes the sign of weight from positive to negative. That's the only difference. Okay. So here we have the situation that what's the maximum speed with which the car can go from top of this curved path. And that maximum speed was constrained by the normal force. That the normal force just have to be 0. If at certain velocity normal force goes to 0, that's the maximum velocity that you can have. Here in this case, if you put the same condition, like what's the maximum or minimum speed that the object can go through this point, okay? In that case, tension have to be 0, because I can show you mathematically how the tension have to be 0, but if you want to find maximum speed at the top, that's one of the questions in your question paper, then tension have to be 0. You substitute tension to be 0 and you find that velocity has exactly this same value. It doesn't really depend on anything else. So if this was my equation for top, and if I put T equal to 0 in this equation, what I get, W, which is mg, equals mv squared by r, and from here you get v equals r times g. Again, it doesn't depend on the mass. Again, it means that if you have an object of 10 pounds or 50 pounds, it doesn't really matter. The only thing that matters is the radius of this circle, like how long spring you are using. That will decide what is the maximum velocity that you can have. Actually, this same rule applies to the curved roads that you see sometimes, that there's a curve in the road. And if you are crossing that road, you will see the road signs that the speed limit has gone down from 65 to, let's say, 35. Why did they do that? They actually use these formulas to calculate what's the maximum speed that you can have at this curve. If you go over that, you're going to skid outside. Same thing, if you go over that, you're going to move outside of this circle. Okay, I said that the tension have to be 0 at this point. If we solve, we can see that if we solve this entire equation, then this equation gives us mg plus t equals mv squared by r. I need a general formula for speed, so this will become mgr, I'm going to multiply r on both sides, plus rt equals mv squared. I can cancel m on both sides, so this will become v squared equals gr plus r divided by m times t. And from here I can calculate velocity as square root plus r divided by m times t. Okay, this is the general formula for speed of this object at the top. Now you look at this formula and you ask yourself, how can I minimize this speed? Okay, how can you minimize this speed? Let's look at each term one by one. First term, first factor is g, acceleration due to gravity, which has a fixed value on earth. You cannot change it. Okay. Second, r, it's the radius of that circle, and once you pick the string, the length of the string, this r is fixed. Okay, so R is also constant. You cannot change anything in the first term. Let's look at the second term. R, it's length of the string. You cannot change it once you have picked. Mass, it's this mass. Once you have chosen your mass, you cannot change it. But then the only factor that can change is tension in the string. And you can change tension by keeping the same length of the string and same mass. Because tension is the force which you are providing when you are moving it in a circular path. And if you move it with more force, the tension is going to be greater. So you can minimize this tension to get some minimum value of speed. And the minimum value of tension can be 0. Okay, it can have some positive value or it can have 0 value. So you set this tension to 0 and you see that this formula is just this formula which I have to. And that was my fundamental point when I said that the minimum speed at the top, you achieve this by setting tension equals 0. It means that your object will barely, if it's moving in this direction, then it will barely go to the top and it will not come back in the circle. It will just fall off, something like this. Okay, but still it will make it to the top with tension 0. But it will not complete a circle. It will just fall off from the other side like this. Okay, and any path. Okay, third question is interesting. It's about Newton's law of gravity, and Newton's law of gravity says that the force that sun exerts on the earth, that's just one example. The force that sun exerts on the earth is the same the force that earth exerts on the sun. It also says that the force that entire earth exerts on this green pointer is the same as this pointer exerts the force on all, like entire earth. Okay, that's it. That's the statement of Newton's law of gravitation. This statement says in general that any object in this world, they exert a force on the other objects, and that force has a certain form, certain mathematical form. But the mutual force is the same. It does not depend on the size of the object. And that's why there are like huge difference between the size of sun and the size of earth, or size of moon and size of earth, but they exert the same mutual force. So the general formula for that one is the general formula for the force that two objects exert on each other is some constant factor g times mass of first object, mass of second object, divided by square root square of the distance between those two objects. Okay, this formula tells us that if you have two objects, this is, let's say, first mass m1 can be sun or any other object, this is a second mass m2, then this object exerts a force on this object in this direction. If this is our first object, this is our second object, then I can call this force F12 as the force exerted on the first object F1 by the second object. Similarly, this first object will also exert a force on this second object. Let's call this F21, force on second object by the first object. And this law says that these two forces should be equal in magnitude. Okay, they wouldn't depend on the sizes of the object, how big or how small those objects are. Okay, and that's why sun is like million times bigger in volume than the earth, but they both exert the same force. Okay, this pointer is nothing compared to the mass of the earth, but still this formula tells us that this pointer exerts the same amount of force on earth as the earth exerts on this pointer. And this raises a very important question, which I will come back to after the question that have been asked. And the first question is the mass of first object, they call it object A. The mass of object A is 2 times the mass of object B. Okay, and both objects exert forces on each other, like the object A exerts force on object B and object B exerts force on object A. Which force will be greater? What do you think? Which force will be greater? That's the question actually. I've just given you the answer. I just told you it doesn't matter how big the objects are, the forces are just equal. That's what I have written. Okay, so it doesn't matter how massive they are, the force on object A due to object B, it will be equal to force on object B due to object A. That's the first part of the problem. Okay, the second part is Where's the second part? Is the acceleration of star A towards B larger than, smaller than, or equal to the acceleration of B towards A? That's important question. That's what I wanted to come to. That if you drop this pointer, you see that this pointer, a marker, it goes in the downward direction, like it falls towards the earth. You don't see earth coming up towards this pointer. Why does that happen? That's this question. And this is the acceleration. And acceleration depends on not only on force from Newton's second law. We have F equals m times A. So if you solve this for A, this is going to be F by m. And you can immediately see that even if both objects exert same forces on each other, acceleration additionally depends on mass. And so the massive object will have a smaller acceleration. So this equation tells us that the acceleration A of which object is massive? Object A is massive, so the acceleration of object B, it will be 2 times the acceleration of object A. And this is exactly the reason why you see your, if I drop this marker, why you see this falling towards the earth and you do not see earth coming up towards this pointer. This is the reason. The acceleration, the quantity that is responsible for fall of this marker, it's the acceleration. And this is the acceleration that you measure. Not the force. The forces are the same, but the acceleration are different. In fact, this marker, when it is falling towards the earth, it actually pulls the earth upward. It actually shakes the earth. It pulls the earth upward. But the acceleration is so small that we barely notice it. But it does. When you jump up from the ground and then you come down, you actually do shake the earth. You actually do shake the earth in its orbit. But the acceleration, that shake, is so small that you cannot measure it or see it with your eyes or whatever, like you see the fall of this pointer. So this is a very important consequence of this law of gravity. Questions? I guess I overrun my time by 1 minute. Thank you.